Welcome to Unit 5, Day 2. So this unit is going to involve a lot of the following equation. Y equals ax squared plus bx plus c. This particular equation is going to be as important to this unit as y equals mx plus b was to previous units. So what does this equation mean? Well, the value of a is going to be whatever coefficient or number that's in front of the x squared term. The value of b is going to be the coefficient or the number that's in front of the x term. And c is going to be any constant number afterwards. The graph of a quadratic relation is called a parabola, and the general shape of a quadratic relation is shown in the sketches below. Now, by changing the values of a, b, and c, we'll change the shape and position of this parabola. So the vertex, it's the pointy end. It's this point right here, sometimes referred to as the optimum value. It could be either a maximum or a minimum value of y. So the vertex, it's also where the graph changes direction. As you can see, it comes down here, and when it reaches the vertex, it starts heading off in a different direction. So this is the vertex. Now, when a parabola opens upwards, the y-coordinate of the vertex represents the minimum value of the function. It is the lowest point on the graph. Okay. Now, this particular parabola opens upwards. And it opens upwards because the value of a is a positive number. So you might want to consider positive being in the shape of a happy face. Anytime a is positive, then the parabola will open up like a happy face. The x-intercepts, sometimes called the zeros, may or may not exist. It all depends on whether the graph crosses the x-axis. And the x-intercepts are the points where the graph crosses the x-axis. So in this case, -1 and 1 would be the x-intercepts, or zeros. In this case, the y-coordinate of the vertex represents the optimum value. It's a maximum. It's the highest point of the graph. This particular parabola opens up downwards, so if we were able to see the relation, it would have a negative a value. So it would be y equals negative a squared, a times x to the exponent 2. The axis of symmetry is a vertical line, an imaginary vertical line that splits the parabola in two. It runs through the vertex and splits the parabola in two. Any point on one side of the parabola, or one arm of the parabola, is reflected equally on the other side of the axis of symmetry. So this is like a mirror image over the axis of symmetry to this part. Unlike the human face, the parabola has a truly symmetrical shape. Again, it's symmetrical on either side of the axis of symmetry. if one arm of the parabola is reflected in the mirror line or the axis of symmetry, the other arm is created. So here we have one arm, and it is reflected in the axis of symmetry. The equation of the axis of symmetry, in this case, take a look at what the x values are for any point along this line. Right here, the value of the line, the x value of the line, is 3. Here, the x value of the line is 3. Anywhere along this line, the x value is 3. So the actual definition of this particular line is x equals 3. Now, talking about x-intercepts, or zeros. The x-intercept, if it exists, is the point or points that the graph crosses or touches the x-axis. So if you look at this particular example, the graph does not cross the x-axis at all. So no zeros, no x-intercepts in this particular graph. In this particular example, the graph touches right on the x-axis at one point. So we'd say that there is a single x-axis. Let me repeat that. There'd be a single x-intercept. That'd be more correct. Here we have this graph, and it crosses the x-axis at 2 points. It crosses it at 2 and 4. So we would say that the x-intercepts are 2 and 4. This parabola crosses the y-axis at the y-intercept. And the y-intercept for the graph shown is 1. At the y-intercept, x has a value of 0. Well, that just kind of stands to reason. Anytime a point is crossing the y-axis, x is always 0. Reflected point. So any point can be reflected in the axis of symmetry. So if you look at this purple line right here, this point right here is 1, 2, 3 units over. And then we have a point that's on the right arm of the parabola. Because this is the axis of symmetry, there is going to be an equal and opposite point 3 units to the left of the axis of symmetry. And this could be said for any point on this parabola. Here, this particular point is 2 units to the left on this arm of the parabola. There is an equal and opposite point reflected in the axis of symmetry that is 2 units to the right. The sign in front of the x to the exponent 2 term determines the direction of the opening. So if this is a positive value, in this case, x to the exponent 2 would have a value of positive 1. Negative x to the exponent 2 would have a value of negative 1. So in this case, we have an example of y equals x squared. X has a positive coefficient, positive 1, and then we get the happy face. Positive number, happy face. Negative number, sad face. So anytime there's a negative coefficient in front of the x squared term, be it negative x or negative 2 in this case, then the parabola will open up downwards. As said before, the parabola changes direction at this point called the vertex. So here we have the parabola going down, and then when we reach the vertex, it changes direction and goes up. In this case, we have a downward facing parabola. It goes up until it reaches the vertex, and then it changes direction and comes back down. In this case, we say the vertex is a maximum value. And in this case, we say the vertex has a minimum value. And the axis of symmetry always passes right through the vertex, right through the middle of the parabola. Again, the axis of symmetry passes right through the middle, right through the vertex, right through the middle of the parabola. So here we have a graph, and we're asked to fill in this chart. First thing we're asked to do is to draw the axis of symmetry and state its equation. Well, in this slide, I've already drawn the axis of symmetry right down through the middle of the parabola, right through the vertex. And the equation for this particular line is x equals 2, because at every point along this imaginary line, x has a value of 1, 2. The zeros, or the x-intercepts as we usually call them, are the points at which the graph crosses the x-axis. It's a little bit hard to see in this example because they don't quite go through a square. They go through the middle of a square or a middle of a unit here, so we have to guess a little bit. But this looks like it's approximately negative 1.2, and this is approximately 5.2. So we'll say that the x-intercepts are negative 1.2 and 5.2. The y-intercept, the point at which the graph crosses the y-axis, is negative 3. The graph slopes upward, and the vertex right here has a coordinate point of 2, negative 5. In this example, once again, we're asked to draw the axis of symmetry. Well, we just find the vertex, the pointy end, and we draw an imaginary line through the vertex, an imaginary vertical line through the vertex and through the middle of the parabola. And at every point along this line, x has a value of negative 1. We don't have any x-intercepts or zeros in this particular example because the graph does not cross the x-axis. So we say these zeros or x-intercepts, we can just put none. or not applicable here. The y-intercept, we can see that the graph crosses the y-axis at a point of 2. So the y-intercept is 2. Our graph opens up upwards, or opens up and out upwards. So we say the direction of the opening is up. And our vertex is right here at the coordinate point -1, 1. In this example, once again, we're asked to draw the axis of symmetry. We find the vertex, and we see that it's right here where x has a value of 4. So this entire line or axis of symmetry is x equals 4. The zeros, or the x-intercepts, well, the graph crosses the x-axis at the point 0 and 8. So the x-intercepts are 0 and 8. Crosses the y-axis at 0. The direction of the parabola, well, it opens down. And the vertex is found at the coordinate point 4, 8.